Banked corners, no friction. So talking about like highways, the way they have a angle on them as you go through the corner, it helps you take the corner. We're going to look at the physics of that. So here's a picture you can use to visualize this. You got these cars that are on this sloped, testing ground, testing track or whatever, and so we're going to look at a no friction situation. So think of a super slippery day, like a freezing rain day or something. And if I drag this over here, you can see the free body diagram for that car. We've got the gravity force and we got the normal force from the track. So if we're looking at analyzing forces, a great first step, of course, would be, drum roll please, free body diagrams, of course, right? So yeah, so we're gonna look at the free body diagram for this thing and go through it, right? And so we're gonna look at the fact that this thing is in uniform circular motion. And so we know that there must be a force towards the center, right? So picture a force towards the center on this thing. I'll make it blue, let's say. Some kind of force towards the center. Well, what force is there towards the center? The only force is really the normal force, right? There's no friction or anything happening. And so really the component of that normal force must be the centripetal force, right? It must be the force that's needed to be in that circular motion. So there we go, just like that. Yeah, so we've got a yellow version of it now. And yeah, so we're just looking at this. Really, it's a centripetal force, remember in the Earth reference frame, this is what we're looking at. In the non-inertial reference frame, you'd swear you're getting pushed outwards by a force, and thank goodness the car is seatbelted in, you're seatbelted into it, and it's pushing towards the center to balance that outward force. Otherwise, you'd quote unquote get thrown outward. In actuality, you would just continue with your current constant velocity, right? So to help visualize the situation, I have a video that I made here of wrong version here, software. So this is a banked corner situation. So this is the banked corner, and it's super slippery. Obviously, the ball, if I let go, it would just roll down. It wouldn't, even if it wasn't rolling, it would slide down with very little friction. Anyway, so I get this thing going with uniform circular motion, and you can see pretty happy to sail along with uniform circular motion without me acting on it or anything once I get it going, right? And the other video I've got is where you might have seen this in a mall or somewhere. Anyways, you might have seen these little wishing well type things, right? And so it's kind of neat. The coin goes in the track here and comes out with a speed sideways, right? And so it comes out with a speed, and it can maintain uniform circular motion for quite a while until friction takes over. Especially if see how long they go there, right? It's quite a while for them to burn off all of that energy that they got from going down this little slope. So those are both uniform circular motion examples for us to visualize, okay? So hopefully, like it says here, it's pretty obvious that there's going to be like a certain speed that's needed for uniform motion, especially, in a case where there's no friction. You either have to have the right speed or, if you're going too fast, it's going to slip out to a larger diameter, or if it's too slow, it's going to fall in, like in that wishing well, right? And with the video of the ball in the dish here, if I spin it too fast, it goes up farther and even flies out across the room if I'm not careful when I'm making it. I video edited that part out though because it was embarrassing. Just kidding. All right, so banked corner, no friction, and let's analyze this, right? So here's the angle we're at, and you want to picture this circle that the object is going in horizontally, okay? So this is a car driving along a highway ramp, and so we got the mass of the car, 1,000 kilograms, we got the radius is 80 meters, and the angle's at 20, and we're going to look at the speed for uniform circular motion. Right away looking at this, you might be thinking, geez, do I need that mass? Like all objects fall at the same rate due to gravity and so on, right? So let's check it out. Acceleration in the y direction, of course, is it stays at a horizontal circle. It's not going up or down, right? So acceleration in the y direction is 0, which means that the net force in the y direction is 0. Well, what forces are there in the y direction? Look at a free body diagram, right? So we've got a free body diagram, certainly have gravity on this thing, excuse me, and there's a normal force perpendicular to the ramp. It's not sinking into the ramp. And so what we know is, since it's not sinking in the ramp, that this upward component here would be equal to gravity. Okay, so that right there, we know that thing's equal to the gravity force, just up instead, obviously, right? So if we're looking at our free body diagram in the y direction, we've got the gravity force, we've got the normal force, y component, adding up to 0, right? So that means the normal force y component is really the normal force times cos of 20. That's our angle there. And so this is one of those situations where it's a little bit backwards. Usually we know the vector and then we find the component by multiplying by cos. In this case, it's the component we know. And so we can work backwards basically and figure out the actual vector itself, which in this case turns out to be 9,800 divided by cos 20. Well, that 9,800 divided by cos 20, what is that? It's mg divided by cos theta, right? Let's keep that in mind. In general, it's just the mass times the gravity divided by cosine of the angle. Yeah, note in this case here, that normal force is bigger than the gravity force, right? The gravity force was whatever, 9,800, right? 9,800 is gravity force. This normal force is bigger. Well, how is that possible? Like, it's because of that circular motion, right? There's an acceleration towards the center, and so in that reference frame, it's, anyways, that's just what's going on. Yeah, so that's providing that. This force right here is providing the uniform circular motion. So that's going to be part of our next analysis. All right, so we know, of course, we've got uniform circular motion. So we have the x component of that normal force has to be the centripetal force, because it's the only force in that direction. For it to be in uniform circular motion, it has to be the case, right? And the only force in that direction, like it says here, is that. And so we've got Fn sine 20, which we already knew what the normal force was. We calculated it out as, that number, right? Well, that's hiding the fact that really that's mg over cos theta. So I've got a combination here of if you're just plugging numbers in, it works. But I mean, it's more powerful to notice that you don't even need the mass and you get these general solutions, general results, which are obviously much more usable going forward, right? So this centripetal force, you have a value because you have a mass, but really the actual force value, you need the mass, right? You'll see later on for velocity, you don't though. Spoiler alert, I guess. So we have the net force, which is that centripetal force. So we can, of course, get the acceleration, F net equals ma, and voila, we end up with, it deletes here for me, that value. That is really just g tan of 20. If you look at the idea of this, you've got the mg cos and then divided by the mg, right? So you just have the sine over the cos stuff. Sine over cos is just tan 20. Okay, so the masses are canceling out because you got an m in here and an m dividing out and so on. So anyways, so now we can say, okay, well, we've got our centripetal acceleration as g tan 20, or as a number, right? So g tan 20, tan of the angle of the ramp, dividing through by the radius, and you get a number or a general result. Square rooting in the end as well. I didn't show it, but I must have done that stuff. Yeah, so that's why this is equal to root of this stuff, right? Root of the g tan 20 and the r, I think I said divide by r, multiplying the r on both sides, right? So there's your r g tan 20 stuff rooted to get rid of the square, and that's your kind of a pretty slick result, right? The speed you need to be the ideal speed, literally just go, okay, what's the radius? What planet are we on? What's the angle of the ramp? What planet are we on for the g value, of course? 9.8 for the Earth. And what's the angle of the ramp? And root that product, and you've got the speed that you need. Okay. So obviously, like someone working for the Ministry of Transportation, right? They might not be as trained in physics as you might think if they're able to calculate these things, because they just know, like, okay, well, the speed limit for the road is 80 kilometers per hour, right? And so they'd have a formula they'd type in and be like, okay, the angle of that, because of the radius of the turn needs to be a certain amount for, really to match the speed that you're kind of supposed to be driving. Or maybe they do it for 95 because they know that everybody goes that speed. Yeah, that is the physics of bank corners. It can seem pretty intimidating and weird, but as long as you follow those kind of steps and you analyze it through, you can get the speeds, you can get the forces, and all that stuff. Okay, so there's a bank corner there. There's just some idea questions there. Yeah, so give those a good try, and of course, once you submit, you get the solutions to help learn from those. I'm hoping people are, following up in the learning process after submitting what you managed to do. Maybe ask for some help, maybe, along the way too. But you submit, and then you make sure to look at those solutions and update your knowledge based on what you see. Learn a little bit more maybe each time. Okay, that's why I'm doing that, of course, to help you learn. All right. Until next time, thanks for watching, and I'll see you later.